So, first of all, I'd like to just discuss a little bit why I think space-time algebra is so awesome. It brings a lot of what would seem to be diverse ideas from quantum physics and relativity all together in one mathematical model. I mean, in the grade 1 vector space, we have the Minkowski metric, we have space-time, although for now it seems to be flat space-time that is treated there. We have, in grade 0, we have the normal, real, scalar numbers. In grade 2, we have the bivectors, which basically it encapsulates all of what we know about the Maxwell tensor, or some say the Faraday tensor, the electromagnetic field tensor. And of course, that encodes the electromagnetic gauge field, which emerges from the U1 symmetry of the Dirac field. And the Dirac field is quantum. And so we go from quantum to special relativity. So what? Well, okay, and then let me just say grade 3, that I haven't explored enough yet. I know it's dual to grade 1, but what is it about grade 3 that sets it apart from grade 1? And what kinds of insights might we get by studying the trivectors that we wouldn't get with vectors? And then there's grade 4. Grade 4 is where the complex numbers come in. Not ad hoc, they're natural. But that's not so much the point of the video right now. The point of the video right now is what about general relativity? I guess my hypothesis is that rather than use the Minkowski metric of flat space-time to create a space-time product in the space-time algebra, let's try putting the Schwartzschild metric in as the underlying operator. What would happen then? Or the Kerr metric, or one of those other exotic metrics of curved space-time. How about we modify the product of space-time algebra in terms of the space-time curvature that is present where at the space-time event that the problem is being solved. Suppose we bring in the curvature to the grade 1 space, generalize it to the 5 different spaces, and then crunch the numbers and see how it affects the quantum mechanics that emerges from the space-time algebra. My gut tells me that the quantum mechanics really only happens with flat space-time. I think that we might be fortunate enough to find that the curvature cancels itself out in the equations or exists way down the line in a series, exists only in the higher order terms, which can then be dismissed from the equation. Certainly, propagation of quantum particles will be affected by space-time curvature, but the propagation in quantum field theory, the propagators, that's for the most part the easy part. The tough mathematics comes with interactions, it seems. But I think in the limit, I think we can take a limit towards a flat space-time metric to incorporate the interactions. I think essentially interactions occur essentially in a flat space-time, and that makes the math much easier. All this, of course, remains to be seen, but it's exciting. So I hope you like this video. If so, hit like. Please subscribe to my channel. Leave a comment below. How would you propose modifying the Minkowski metric to include curvature in the space-time algebra? Leave your comments below.